first off, before we go on to any other one, questions that you guys have about protons, neutrons, electrons, atomic mass, mass number, anything that I can clarify before we go on?
What is the one? Okay. I just don't remember them. I just need to memorize them.
Well, yeah, a lot of that is just knowing the different terminology between them.
Like there's one where you like subtract.
That's mass number. So mass number is protons plus neutrons. Okay? And so if you have the mass number and you know the number of protons, then you can subtract those two and get the number of neutrons. That's just basic. You just need to know the difference in those. The part that I think you guys really struggle with is really knowing what an isotope is.
Yeah, I don't know what that is.
Okay. So, and this is stuff that's in your notes, but an isotope is atoms of the same element with different mass numbers. Now, what does that really mean? Well, it's like mass numbers. It can mean a number of things, and this is the probably most formal definition that you guys will see, but mass number, we know, is the number of protons plus the number of neutrons. And can you see that blue marker on there? Okay. That's by definition what that is. So theoretically, does the protons in your atom ever change? No, because that's what identifies your atom as your atom. So what's the only real thing that changes? Your neutrons, right? So you could say this definition is atoms of the same element with different number of neutrons even. Okay? But isotopes, for example, chlorine-35 and chlorine-37, both have how many protons? We'll look on your periodic table. Chloron period, chlorine, not chloron, chlorine is 17, right? So regardless if it's chlorine-35 or chlorine-37, it still has 17 protons. That's what identifies it.
So the neutrons is the only thing that changes?
The neutrons right here is the only thing that changes. And the neutrons is based off this number, which is the mass number, right? So 35 minus 17 is how much?
18.
18? And then 37 minus 17 is 20. Is it still chlorine? Yes, but the mass, even though these are neutrally charged, the mass is the only thing that's changing here. Now, when you get an element of chlorine, it's going to be a sample that includes both chlorine-35 atoms and chlorine-37 atoms. That's where we get isotopes. These are isotopes of each other. Okay, so if I had a sample of chlorine, parts of that sample may have some of these atoms in there. Some of them may have the chlorine-37. That make sense? And that's where we get into these more technical terms about percent abundance and actual isotopic mass. Because this chlorine-35, and I'm making this number up, this right here may actually weigh 34.9878 AMUs, right? This one may be 37.0012. I made that number up, it's not correct, but each individual atom may have its own mass, may have its own weight, and then how often it occurs in nature. Let's say this one occurs 85% of the time. How much would this one have to occur? Well, 100 minus 85. That makes sense? Could exist 50-50, it could exist 80-20, and that's why in these types of problems they give you a percent abundance for those. Does that kind of clarify a little bit on my steps? Okay. So first example, let me just go back through the process really quick on calculating average atomic mass. Average atomic mass is the mass that we get from the periodic table, right? All of the homework on this worksheet, you're calculating that number. Is it on the periodic table? Yes. You could probably look at the periodic table and compare, but based on the data that's given, your task will be to calculate that. So on this first one, there were two isotopes. It's going to follow this pattern, two sets of parentheses. Within that set of parentheses, you're going to be multiplying the percent abundance times the mass of the isotope. Percent abundance times the mass of the isotope.
Is that the formula? Or is that
This is the same pattern. And when you do those, however many isotopes there are, if there were 3 isotopes, you'd have 3 sets of parentheses. That formula will give you the average atomic mass. This number is on the periodic table. That's how all of those numbers were calculated, by looking at the isotopes of that element and calculating it. Okay? So first example in our notes, we don't know the atom, but we do know that this first isotope exists 72.15% of the time. So we have to turn that into a decimal, okay? Because we don't use percentages when we multiply. So we move it over 2 places to the left, and we multiply it by that individual mass, which is 84.9118. And then we take the second isotope, if there's just 2, take the percentage, 27.85, we turn it into a decimal, and we multiply it by its mass. Now these are pretty straightforward when it asks you to find average atomic mass, because you have to be given that set of data. And at this point, once you set it up, you literally just type it into the calculator. And then keep your answer to 2 decimal places, okay? So were there any problems on your homework 1, 3, 4, 5, 6, and 7? All of those should have that same format. Literally, you're just taking the number, the information in the problem, plugging it in, and typing it into your calculator as seen. I would avoid doing these in pieces. Once you write this out, you guys have fancy enough calculators that you can do open parentheses, number times number, close parentheses, plus open parentheses, and do it all in at one swoop so that you don't have any errors. Any questions on those? Yeah, you have a little different calculator. Now, we did not do this example in class, correct?
Correct.
Okay, so let's work on this. Now, most of your problems will look like this. And all of these problems, regardless, will still have that same format. And so problem number 2 says magnesium has 3 naturally occurring isotopes. This is the first isotope, magnesium-24. It exists at 78.99% and has an isotopic mass of this. The second isotope, magnesium-25, exists this often and has this mass. And then this is the third isotope. It says determine the percent abundance and the isotopic mass of that third isotope. Well, a couple of things we can take away from that is, since there's 3 isotopes, how many parentheses sets are we going to have? 3. That's a pattern that will stay through all of these. Okay, this first isotope, and really does it matter what or where you put the isotope? No. This first isotope, let's look at magnesium-24. How often does it appear? 78.99. So if we want to put that in decimal form, we move the decimal over twice. We get 0.7899 times its mass of 23.9850. Right? The second isotope, magnesium-25, is 10%. So if we move it into decimal form, we're going to put 0.1, or you can add all the zeros in, that's fine, times 24.9858, and then magnesium-26. Now, did they give us any information on magnesium-26? No. And even in the problem statement, they're wanting us to find the percent abundance and the mass. So we're essentially finding these 2 spots. Now that's going to be really hard to do if we don't have some more information. Now, this entire formula, if we had that information, would give us what? The average atomic mass, right? Where do we find all average atomic masses? From your periodic table. So, for this problem, since you know the element, find magnesium on your periodic table. And since we're not calculating that, we can just take that mass off of the periodic table and use it in our formula right here. Because essentially all of these numbers worked out would add up to that number on the periodic table. So what do you guys get?
So you use 24 and
You're going to use the entire number on that periodic table. So 24.3050, right? Now, we still have two pieces of information that we need to find. So let's take a side step. Let's think about what percent abundance would mean. If my percentages were 50, 50, what would that add up to? 100, right? If I had 32 plus 33 plus 34, I think that's right. No, 34 and 34. What would that add up to? I think that adds up to 100. Yeah, 100, right? So, as long as we know one of the two or two of the three percentages, can we not find out that third one? We know that our first isotope exists 78.99%. This one exists 10%. So, can we not find the percent that this third one came up with? Subtract, well, I would do 100 minus 78.99 minus 10. And what you should get is 11.01. So we know that this third isotope exists 11.01%. Now if we use it in our math formula, what do we have to do to the percentage? We need to move the decimal over, right, to 0.1101. And then now, how many spots now do we need to find? Just one, right? So we can designate this as some value x. Okay? Now, look at your problem. Is that not just a simple algebra problem? Well, it doesn't look simple because there's decimals, but is that not just an algebra problem? We've got a number equals a number plus a number plus a number x, right? So to simplify down to x, we're going to have to do some math here. You can do this multiple ways, but you need to show all steps. Some people will take this number here and this number and go ahead and figure out what that is. So using your calculator, use parentheses. Let's take parentheses 0.7899 times 23.9850, close parentheses. So good?
Mm-hmm.
Okay. Plus parentheses 0.1 times that number, and let's figure out what this portion here represents. Everything else will copy down the same, and this will essentially be 0.1101x. So somebody that has their calculator, if you'll find that out for me.
21.4443.
Say that one. 21.4443. Okay, and keep enough decimals. 4 is plenty, but keep enough so that rounding issues aren't going to be a problem. Okay, now that you've simplified this, how do we get our x term by itself? We need to subtract this from both sides, right? Here it cancels. Figure out what 24.3050 minus this are. Now keep in mind, guys, they're talking about, we're recording, so everything you're saying, it's picking up. Okay. So type that in, Cameron, or Lydia, or whoever the calculator. That's okay. Just one of you guys. This portion, 24.3050 minus
2.8607.
2.8607. Right, and this is going to be equal to what's left over of 0.1101x. Now, how do we get x by itself? Divide. So this is just it's a simple algebra problem, multi-step algebra problem. You're dealing with decimals here, but you guys have access to the calculator. So as long as you're showing your work and keeping up with decimals, it should be fine. So 2.8607 divided by 0.1101. 25.9, keep 2 decimal places.
98, so
25.998.
It's 25.98.
That's fine.
So you wouldn't make.
Well, that's 2 decimal places.
Okay.
What was that third number?
2.
Okay, then. So 25.98, and then what unit do we have here? A and here. So this is the mass of magnesium 26 isotope. Now this is how number 2 and number 8 on your homework should have been completed. And you guys, I don't think, did that yet, so we are going to take about 5 minutes to do that. Okay, and you can go ahead and push stop, Jason. Or I'll push it. Right now. No, we're gonna go ahead and push